thank you very much for the invitation and the introduction. So, I mean, the workshop is here because you organize it. So we only provide a support letter as a TC, and we are very happy that the community is organizing workshops like this one. So, and thanks also for the invite. Yeah, and good afternoon, everyone. So today I'm going to be talking about motion planning. So within my group, we work at different levels of planning, motion planning, multi-robot coordination, and also task planning and allocation for multiple robots. And we mostly focus on environments shared with other robots and humans. But today I will focus on motion planning, and this is work mostly done by 3 PhD students of the group, Bruno Brito, Lasse Peters, and Elia Trevisan. Okay, now it's working. Okay, so, well, this is a video recorded from a car driven by a human. So we cannot do this yet with a self-driving car, but it can give you an idea of how complex it will be for our robots or our self-driving cars to navigate in complex environments shared with humans. So this is the city of Delft. This car will have to be reasoning about what's happening in real time with the other agents, right? So is that van going to let me pass or go in front? What are those pedestrians and bikers doing? And it's going up and down bridges. And these are very narrow streets. So we normally say self-driving cars in the Netherlands maybe is one of the last places where we will have them due to this very high complexity of interactions that happen in real time. But nonetheless, the car will have to move safely. And similar challenges also appear where you have mobile robots in environments shared with humans, indoors or factories or hospitals. So, well, I mean, we are in robotics, we all know how this works, right? It's our autonomous vehicle or robot. It's an environment shared with other agents. It has some perception module that perceives the environment. It makes some predictions of what everyone else is doing in the environment. Those predictions then hopefully multimodal with different hypotheses and weights go into the motion planner that then controls our robot or car. In particular, I'm going to be using a lot of trajectory optimization, model predictive control, and different variants of that in this talk. There are, of course, other ways to do planning as well, but that's the one that we favor. So yeah, I think MPC by now almost everyone knows it, or everyone. Many use it in the literature, right? So we optimize a cost function with a number of time steps in the future from the current time to a horizon n in the future is discrete time steps. And we have our state, typically x, and our input, typically u for that along that horizon. And then that cost function could be anything like minimizing the deviation with respect to a reference path. We have a set of constraints, the dynamic model of your vehicle. We also have the interesting constraints for avoiding other agents. And that's the one that makes this problem interesting. And that's where also the interaction with others comes into play. And nowadays, there are many efficient solvers like Acado, Acados, Forces Pro that can solve this. So this is work from our group from a number of years ago for a quadrotor and also a self-driving car avoiding a person. And in the background, these two are using an MPC that is being solved in real time for these robots. And as I was saying, many of us are using such a framework nowadays due to its power. But yeah, there are still many challenges for the real world application. So some of them are how do you deal with uncertainties because the world is not deterministic. How do you also provide guidance to such a planner because this is a local planner for a few seconds in the future. So how do you provide more complex global guidance? And the last one is how do you model interaction with other agents? So we are working in all those three challenges. In today's talk, I will only focus on the interaction. If you're interested about the other two, I'll be happy to discuss it in a break. Yeah, so interaction. Here another example of the Netherlands, a very nice interaction. If you ever drive a bike in the Netherlands or you're a pedestrian crossing a bike path, good luck. So this is a normal day with bicycles, and you can see that humans are very good at reasoning about what's going on. What will the others do or not do? Well, someone got stuck in the middle, can also happen, right? So you probably need to reason about the different possible futures. So this is real. I mean, we need to model interaction, right, for real world robotics. And the interaction in this picture, the way it comes is because the actions of our robot will have an influence also on the other agents in that environment. And that needs to be taken taken into account here by closing this loop, right? So the perception should also be informed by the plan that we are computing, and vice versa. The planner should also be informed by the perception, because these two are coupled. So the actions that we plan for our robot will also have an influence on what the others do in that environment. So that's the complex coupling that happens when modeling interaction. And yeah, so now the thing is that this optimization problem, you can still formulate it as a receding horizon problem, so model predictive. And here now you will have both your states and actions, as well as the states and actions of everyone else in that environment, right? So that's what you see there, the cost function and also the constraints. They depend on both your state and actions and the other agent's state and actions. And then you will need to make some assumptions about this to be able to solve it. This looks like a centralized problem, but in practice, every robot will solve this problem itself and then execute it. So it's making predictions for the others implicitly. So how do we solve this? That's what I will be dealing with in the remainder of the talk. And I will explain three possible options that we have explored in our group. So the first one is to say we don't really want to model explicitly interaction. Maybe we want to take an easy route in some sense. We are just going to learn a cost function, and that one is the one that models interaction implicitly. And it will be, in particular, what we did was for a vehicle that merges into a lane full of other vehicles. So this can be a challenging, crowded scenario where you need to make gap, right? So your self-driving car will have to negotiate in some way with the other agents to make them enlarge a gap so that it can safely merge. And here it will look at things like what's the speed of the other agents, are they accelerating, decelerating, what's the time to collision, and how is this gap changing over time. So those are the features that one can look at. So what we did was to train a neural network. So that's the cost function that this neural network will provide a reference velocity for the agent. And that reference velocity is then tracked by a standard MPC. So our model predictive controller is controlling the robot with constraints, so it's still safe, but it tries to follow a reference that comes from the deep neural network. And that one is kind of an intuition that tells go faster, go slower, try to merge, don't try to merge, but the MPC will still make this safely. And we train that one with, well, we reward making progress, right? So we want the vehicle to merge into the traffic, and we penalize things like collisions. And we train it in environments with interaction, where we sample different behaviors for other agents in the traffic lane. And that could be more or less cooperative. So for that, we use an adaptation of an intelligent driver model to simulate the other vehicles. And that is also a difficult topic when doing this. How do you model other agents in simulation? But that's a question for maybe the discussion or another day. But what we did there was to use that model and then sample different parameters for the level of cooperation. And here's some results of that. So here, our self-driving car is the one in yellow that wants to merge into this lane with traffic. And the red cars with low numbers are non-cooperative, and the high numbers, green cars, those are the more cooperative ones. And what we see is that our vehicle is capable of nudging its way somehow. We don't exactly know how, because this is a neural network that is providing a reference velocity. So the neural network is telling accelerate, decelerate, and based on the observation of the other agents on the lane. And then the MPC is avoiding the collision. So we can say that this was safer than just using learning per se, and the behavior and performance was also stronger than standard MPC. In part because in MPC you have to tune it, so either you tune it the MPC to be very aggressive, and then you will have a lot of collisions, or you tune your MPC to be conservative so that you don't have collisions, but then it will never merge, right? Because it will not open a gap. So by doing the combination, you can take the best of both worlds in some sense. Now, yeah, this is very nice. So then the nice thing is that you can learn this cost function that otherwise will be very difficult to do by hand. And you can still have the guarantees from the low-level controller. But we are not modeling real interaction, so it's only implicitly done. It doesn't really appear on the optimization itself. So it's just a black box in some sense, providing guidance. So next, I will discuss some ways to explicitly model interactions. So the first one is to have interaction-aware predictions. And then here, we want to solve this original problem, right? Where we have a joint optimization problem where we also compute predictions for the other agents. And the observation that we made here was that we can also solve an MPC problem by sampling. So that's a sampling-based MPC or MPPI, how it's mostly referred in the literature nowadays. And there, the way it works for those that are not familiar yet with MPPI or sampling-based MPC, what we do is we have an initial trajectory. That's the one in red there in that image, our robot. And this is a boat now because that project is for autonomous boats. But yeah, it doesn't matter what type of robot you have. And it wants to navigate towards a goal. So then the first thing that we do is we will sample a set of inputs, control inputs, and we can sample many of these control inputs. So you can sample hundreds of sequences of control inputs from a distribution. And those you forward simulate them, and that's going to give you these different trajectories. So one for each sequence of inputs that you are sampling. And you will have hundreds of these. Now you have to compute weights for them. So you are going to compute weights depending on how good they are with respect to a cost function that you have designed, or whether they are in collision, and so on. So that's the weights, and then you do a weighted sum of those different samples that you got. And the trajectory that you will execute is the one given by the weighted sum of the trajectories that you sample. So those that are better will have very high weights, and those that are very bad will have low weights. And for the next time step, what you will do, well, now like in MPC, your robot will execute part of this plan, so the first input, and then you will update your sampling distribution based on the weights that you computed in this iteration. And you keep doing that again and again, and your robot will move towards the goal in a safe manner, hopefully. And then, so that's how MPPI works in the high level or sampling-based MPC. Now, the nice thing of such a method is that that you can have arbitrary cost function and constraints. So you don't need things to be differentiable anymore, like when you use a solver for MPC, that you need things to be differentiable. So here you can have anything. So you can have, for example, rules that are non-differentiable. You can have a complex map and so on, and it's okay because you are going to collision check and evaluate those samples independently. You can parallelize it on a GPU or the CPUs, and that makes it very fast. So what we did was to then model interaction by sampling. And the idea is that then we will not only sample for our robot or car, but we are also going to sample for other agents in the environment. So what we do is, basically you have your, let's say, 2 or 3 or n agents. And what you are going to do is you formulate the centralized problem where you have the state and inputs for all the robots. And in a smart way, you take samples for, well, first you initialize the goals. So you need to guess where the other ones are going because this is distributed. So you first need some estimator that tells you where is the other one going. The easiest way is a constant velocity model, but you could also train a neural network to predict that goal of the other agents. Then you are going to plan a motion for every agent in the environment by taking random samples, a sequence of random samples of the control inputs, and then doing this weighted sum as I was explaining before. But you do that for every agent in the environment in a smart manner. And then you will apply the first input to the robot. The one for the other agents is just a prediction. I mean, they do whatever they want themselves, but you have a prediction, an interaction-aware prediction for them. And then you again iterate over time, right? So here one example. This is with 4, so 3 autonomous, 3 boats and our autonomous boat in orange. So all of them are using this algorithm in a distributed manner. So all of them are running this interaction-aware MPPI, and they all compute a trajectory from themselves and predictions for the others based on that reference goal that they are predicting. And you can see that, well, in this one, in the paper, you have all the details, but the standard MPC will be here leading to a deadlock. So didn't really resolve it nicely. But with MPPI, thanks to this interaction-aware sampling of trajectories, you get that behavior that some will make room for the others so that they can all nicely interact. So, yeah. So that was for the interaction-aware MPPI. And yeah, too fast. Sorry. Yeah. So now one challenge that you have with these sampling-based methods is that the performance you get is very much influenced by the distribution of samples that you use. So for instance, if you use a very wide distribution of samples in MPPI, you could be conservative, or your motion could not be great because you are taking then the weighted sum of all of them. And if you take a very narrow distribution, your performance will be very good as long as that distribution is good. But if something unexpected happens, then all your samples can be wrong, invalid, like what happens here. So this robot is moving, and what you see there are the sample trajectories for different time steps. And something unexpected happens that breaks all of them. And then in this case, MPPI will not know what to do because all the samples are wrong, are in collision. And it needs to do a weighted sum. So this illustrates that the sampling distribution that you use for this method is very important. So what we also did was to then take always some sample from a different controller. So one nice thing we have is that we are engineers. We have developed planners and controllers for a long time. So you could always add 1 or 2 samples that are from a hand-designed planner. In this case, one of them is just stopping or slowing down. So that will be one sample that you always add to your distribution. It's only one sample, so it doesn't change much the result because then you do the weighted sum. But what is nice is that when something unexpected happens, that one sample that is still safe then gets a very high weight, and then it can bias your distribution to something that will work again. So that's why in this case, with these ancillary controllers, we were able to adapt when something unexpected happens. Now, so that's the second way that I wanted to present. It's to compute an interaction-aware prediction for your planner. And in that case, we did it with sampling-based. There are other ways to do it as well, with sampling-based MPPI or sampling-based MPC. And the last, the nice thing is that, yeah, now we explicitly model interaction because we have the interaction in the cost function, and we are making and computing predictions for all other agents in the environment, and then adding those as constraints in our optimization problem, right? You have some challenges there, like sample efficiency and design, and also that we are only computing one trajectory. So that's the next one that I will address. But there is also a big field of literature that it's really explicitly solving this interaction problem. At the end of the day, this is a dynamic game, right? And you will have to solve this game, right? So this dynamic game. And one thing that we look at was how do you also account for multiple hypotheses? And that's what I will be explaining next. How am I doing with time? I think so, still fine. Okay, so here you have one example of why do you need to reason about multiple hypotheses. So here that human was just crossing, right? And you will just make your prediction that he's crossing very fast. He's just going to the left, right? Let's play it again. So you will just say, okay, I can pass on the right side, it's all safe. But then he stops and turns around and comes back to the right, which is rather unexpected, right? So that you need to keep those two hypotheses with different weights. And that's, yeah, so here when the pedestrian comes there, then you think that it's going left, but at the end it goes right. So you want to account for multiple possible futures when you do contingency planning. So in the morning, there was also a speaker that was talking about contingency planning. So that's, so now there are some aspects that real world interaction that one needs to take into account here. And these are so the actions and how they behave, right? And you need to account for uncertainty. That the uncertainty in this case comes from you don't know exactly which of the possible futures they will follow. Will they go right? Will they go left? And in that case, you will need to account for, so plan with contingencies, right? If something unexpected happens, or if it goes to the mode that is lower probability, you should still be able to react to it safely. So we formalized that this kind of reasoning by introducing this contingency games approach. And it's a mathematical framework that comes from the dynamic games theory, and then plans for the contingency planning in that framework. So how does it work? So we want to minimize computer trajectory for, again, so for both agents. So the H will be the human in this case, and that is the robot. So we optimize, we solve a joint problem. The robot solves a joint problem to get both a prediction and a plan. And that's the state and the control trajectory. And then we minimize a cost function that depends on both. Will depend on our robot, but also on the other agents. And you do this subject to a set of constraints. So you want to avoid the collisions. You could have other constraints, but the pairing ones are the constraints that you want to avoid a collision, right? Those affect both agents, your robot and the obstacle. And you solve this problem for both the robot and the human, so the other agent. So both of them are going to solve this couple problem. And when you solve that optimization problem, you get the trajectory for both your robot as well as the human. The one for the human is just a prediction, and the one of the robot is the one that you actually end up executing. And you do this in a receding horizon fashion, like in MPC that I was explaining before. And this is also called predictive gameplay, model predictive gameplay. How am I doing with time? Because we started a bit late, so I'm not sure. Sorry? Okay. Okay, so then the challenge here is that the intents are not known, right? You don't know exactly what they will do, so that appears in the cost function. And here in the video that I showed before, those intents was whether this human is going to go forward or it will turn around and go back, right? So whether they go right or left, in many cases you don't know. And so what you can do is you can parameterize them. So you can say there is a finite set of different behaviors, and each of them we are going to parameterize it by this theta that you see there. So a parameter, one could be going left, the other one could be going right. So you will have those two parameters in this case. And you will need to maintain a belief over that parameter. And that belief, you could keep it with a particle filter or a UKF. I will not get into details on how we keep the belief of that parameter. Let's assume you have that given, that someone can compute what are the different hypotheses and what's the probability of each of them, or the likelihood of each of them. And then this is what you will use in your cost function. So that belief over the different hypotheses. Now, there is a spectrum of here. So one that we typically do in planning will be to just take the maximum likelihood. So here you will say the most likely is going right. So I'm going to only take that into account, and I'm going to plan a trajectory that avoids the right. So that we have used it a lot in game theory when solving games in the past. On the other hand of the spectrum, you could, so that's taking that maximum there. And then on the other hand of the spectrum, well, okay, so that's there are efficient solvers for that, and it's potentially unsafe. On the other side of the spectrum, you can plan in expectation. And when you plan in expectation, what you are saying is I'm going to compute a trajectory that does 0.5 one, 0.5 the other one, right? Avoidance, if that is the weights that you have. So what can happen if you do that is that this could be conservative. So on that side, you will be safe in the sense that you are avoiding everything with that probability distribution that you have at that point, but your robot could become very conservative. So for example, in a case that you have 50-50 for going left or right, your robot might just go straight, slowing down because it doesn't really know what to do. So that one accounts for uncertainty, but there is no future information gain, so it can be conservative. And that's where this contingency planning comes into play. So it's somewhere in between that what you assume is that you are going to get certainty at some point in the future. So at some point in the future, you will know whether that agent goes left or right, and that you exploit that during the planning. Let's skip this. Yeah, so basically the way it works is contingency planning. You will have one trajectory before that branching time at TB, and that one needs to be consistent for all possible futures. And then after that branching time, you will have separate plans that you compute for each hypothesis. So you will have one plan for going left, one plan for going avoiding on the right or the left, right? And this needs to be consistent. So you make it consistent by formulating your optimization problem, where you are going to keep separate predictions for the other agent, the human in this case. So you are going to compute a trajectory assuming that the human goes right, and a trajectory assuming that the human goes left. And then, but you have a weighted of these ones, right? So you account for the weights of each of them. So that's the probability distribution that we have. And then we are going to optimize for that, subject to the constraints that the trajectory for our robots, so the trajectories that we compute, all of them need to be safe. And the coupling comes here. So for the horizon until the TV, there we are saying that all the trajectories need to be the same because they all need to avoid, because you don't know yet what is going to happen, right? And you want to be able to react to any future possible future at that time TV. And after that time, you assume that you will have perfect knowledge of what is happening, and then you commit to one of them. So after TV, each of them only needs to account or avoid one of those predictions. And yeah, let's not get into more details of this in light of time. And then the way that you solve this is basically you, like in dynamic games, you will formulate this joint optimization problem with the KKT conditions, and you have all the details in the paper. And there are very fast solvers nowadays that can solve these dynamic games. And in the animation, you see how these trajectories look like. So depending on the prediction that model that you have for the agent, you see that it's getting biased more towards the right or the left. Your black plan, that's the contingent plan. And that depends on the prediction model that you have for the other agent. And then at some point, your vehicle will commit after that point to one or the other based on the observation at that point. So maybe let's just skip the results and let's go directly to the summary. So in summary, what I explained different methods for how to model interaction in motion planning, interaction between the robot and other agents in that environment. The first way that we look at was to learn a cost function. We want to use a standard planner that we already have, could be MPC, but could be any other planner that you have. And computing that, designing a cost function that models interaction could be very complex, right? So what you can do is you can learn that cost function. You can use a neural network and reinforcement learning to train that cost function, and then use it with your favorite planner. Then the second way that I explained that was then explicitly modeling the interaction. So we were making a prediction for the other agents and a plan for our robot. And then one way to solve that is by sampling trajectories for both the other agents and your robot. And we use MPPIs, interaction-aware MPPIs, so sampling-based MPC, which has the nice property that you can have any cost function and constraints because you're sampling and collision checking. And then the last one that I explained was these contingent games, where all these is a dynamic game. So then we look at how can you formulate this dynamic game and solve it in real time, and how can you plan for these multiple hypotheses so that you are robust to multiple futures. There are still some challenges, right? So how do you infer the objective of other agents? That's a cost function that still appears there. And if you're interested in that, you have to look at inverse games. So we also have some work in inverse games. But yeah, I didn't have time to go over that today. And the code for all these three things is open source. You can find it also on our website. And advertisement, we are organizing RSS in July in Delft. So hopefully many of you will be there, and I'll see you in Delft. We'll be happy to welcome you there. And I'm happy to also take questions. Thanks.
Great talk, Javier. So we have time for questions. You can go up to the mic.
Thank you, Professor, for your presentation. So I have read through your paper about this game,
Yeah.
which is very impressive. But I see that there's something missing. That is the computation efficiency of actually how fast you can solve that game for the optimal condition. So would you please explain what is exactly the computation efficiency of the solver of the conditions game?
Yeah, so it's real time. So I'm sorry if we didn't report the computational time in that paper. So we try to report the time, the computing time in every paper. That it does run real time, and we also have a version working on the robots. So we have multiple Jackal robots in the lab. So we are now running it also in real time with the robots. What we also have done that is work in progress, we are also training, you can also learn the function. So we are also looking at speeding up these solvers by training a policy from the game. So that's a speed up. But even then, it's already real time. So it's slower than the standard MPC, but it's still running real time. So you can have 10 hertz or higher on a computer, let's say a laptop. Yeah.
We have time for one. Thank you for the great talk. I guess I have two questions. One on the first part where you learn this reference velocity. Do you also learn the parameters of the cost function in the MPC, like the Q and R matrices, or are those hard coded and you just learn the reference?
Yeah, so in the first work that I explained, we just learned the reference. And that's, yeah, because so in MPC, you have all these different weights, right? So that is also, we wanted also to be able to penalize control inputs and so that it doesn't shoot too much the control inputs and things like those. So those were still in there. So it was only the reference that we were learning, not the whole cost function. So it was just one time.
The question was in contingency planning, how does this scale with multiple agents? Because you have this like combinatoric with the number of possible modes. If you have multiple agents, each with multiple modes, have you explored that, or what are your thoughts on the scalability?
Yeah, so, and well, coming back to the previous question, so I mean, it's a very interesting problem also to learn the whole cost function. So that's definitely interesting, and we are also interested on doing that, but it gets much more challenging for stability. Now, for your question about the scalability, so we did implement it with 3 agents, and those results are also in the paper, I believe. So to that extent, it's scalable. Of course, if you go to much higher numbers, like 10 agents and so on, then this doesn't work anymore. But what you can always do is to only take the closest ones. And then the other thing you can do is to learn, right? So that's what I was hinting to the previous question. So we did this a little bit in an RSS paper 2 years ago, and we are working on a journal paper of that. It's called Lamotized Games, where what we are doing is to train a policy with the game, and then you can execute that policy or use that as to warm start the solver. And that way you can have an order 10 magnitude acceleration of your solvers and so on. But yeah, yeah.
Thank you.
Yeah, I also have two questions. Thank you so much for the talk. One question is two questions on continuous game. One question is so since you are considering the human robot system, so for example, the robot is optimizing some objective, and the human also optimize some objective, and after some iteration, probably we can converge to generalize machine driven. But the assumption is human is also really do some optimization problem, but in reality, the human has boundary rationality. So I'm wondering if this kind of both side optimization is a good problem solution setup for human robot system.
Yes, I mean, yes and no. So, I mean, this is something I wonder also or worry. So, I mean, there are people that, like our collaborators in those papers. So, there are ways to also add the uncertainty into the game formulation to some extent. But it is true that you're assuming rationality. You're also assuming that the other agent is going to execute the plan that you compute, right? So that's implicit to that model. At least when you do contingency planning, you can have multiple futures. So you could also have a plan that is that it doesn't react, right? So that could be one of your hypotheses. But that's also a reason why we are also working on other frameworks like the MPPI that I showed before and so on. So my hope is that at some point we can compare them and have a better answer for that. Because if you don't do the planning like this, you're also making an assumption that is that they don't react to you, right? So ideally, you need to account for everything. You need to account that they might react, they might comply, they might be cooperative, but they might not be. So you will need a wider spectrum of hypotheses. Yeah, and maybe it's even a continuous of multiple hypotheses. So yeah, it's still an open problem.
I know there are more questions there, but it's very interesting talk. But I think to keep it time, thank you once again.